Hi guys, welcome back. So we're going to do some complex familiar examples today for integration by parts. Now, just as a little reminder, we're going to use this acronym LIATE to pick our U term, and this is the formula that we are looking to use here. So let's go ahead. This term here, x minus 1, that's going to be an algebraic term. Sine of x is going to be a trig term, and so therefore we're going to pick x minus 1 as our U term. So what this means is that the derivative of v, this is going to be our sine x term. Okay, so now what we need to do is we need to derive u and we need to integrate v. And now all we need to do is we just need to substitute into our integration by parts formula. So when we have an integral in the form u prime v, okay, which is what we have here, then we are going to find the solution or the integral of that by multiplying u and v together, take away the integral of v u prime. So let's go ahead and let's substitute those values in that we've now defined. So the integral of x minus 1 multiplied by sine x dx, and that's going to be equal to u times by v. So x minus 1 times by negative cos x minus the integral of v, which is negative cos x, times by the derivative of u, which is just going to be 1. So let's go ahead and finish up this question. And there we go. So the last thing that we could do is we could go ahead if we wanted to, and we could factorize out that cos x. I don't think that's going to make too much of a difference to our solution there. And then I've also just got to add my constant on the end. So complex familiar, I don't know if I would actually call this a complex familiar. Maybe this is a more simple familiar question. Let's jump in with something a little bit trickier. So I've grabbed question 9. This is 9b from page 378. And again, we're just going to use our little LIATE acronym here. So first of all, we've got our x term, and x is always going to be algebraic. And then we've got e to the x, which is going to be our exponential term. So therefore, we're going to actually pick x as our value for u. And then therefore, that means 1 over e to the x dx is going to be our value for prime v. Okay, so let's go ahead. We need to derive this function here. So u is equal to x. The derivative of that is nice and simple, just going to be 1. And then we need to find the integral of this function here. So we can just use the chain rule to do that if we so wish. But this is probably pretty simple to see that this is going to be negative e to the negative x plus our constant. So let's go ahead and let's substitute those into our function for integration by parts. So now let's go ahead, let's expand these brackets out and let's perform this integration. So again, when we integrate this a second time, I hope that we can appreciate that this is just going to become e to the power of negative x again. That's the really nice thing about these exponential functions, which is why we tend to want to pick them to be the one that we integrate. So just as a little refresh of that tip from the last video, when we're picking u, we want to pick something that's going to be easy to derive. And when we are picking v, we want to pick something that's not going to become harder by integration. All right, so let's go ahead and finish this off. Okay, so all I've done, I've got the negative integral of this function here, and then I've factorized out negative e to the power of negative x to get my particular solution plus the constant on the end. Let's do one more trickier example. Last one, I've got my formula over on this side. I've got my tips for picking u here. Now we've got a logarithmic function. So this is going to be our first one here, L. And then we have our algebraic term on the bottom here. So I'm going to pick ln x to be my u. And that means 1 over x dx is going to be my prime v. Okay, so as we just said, I've gone in, I've defined my u, and then I found its derivative, I found my derivative of v, and then I found the integral of that, and I've substituted it into my formula. Now, what you're noticing, or what you may notice here, is that we actually have a very similar issue. So this is the thing that I'm actually trying to find the original integral of. So what I'm going to do, just to make this hopefully a little bit clearer for you, if I let the integral of ln over x, or sorry, it should be ln x dx, and I'll let that equal to a, then I have a is equal to ln squared, because I've got ln times ln, minus a. So I hope that you can appreciate that sort of substitution there, because otherwise there's not going to be really any way to simplify this, because we're just going to keep going down and down and down and finding the same thing over and over and over again. But what we can do now, if I add that other a to that side, I'm going to get ln squared x, and now I'm going to divide both sides by 2, and then I'm going to resubstitute in the a there. So the integral of ln x over x dx is actually going to be equal to ln squared x over 2 plus c. Nice little one there for you. So if you want to check this answer in the back of the book, please be my guest. I have gone on and I have double checked with that online calculator, and I have gotten that correct. So I hope you enjoyed this one. This is some more complex type examples with some nice little algebra substitutions there at the end. In the next video, we're going to go ahead and we're going to have a look at integration using partial fraction decomposition. So if you haven't already checked out my video on partial fraction decomp, please go ahead and do that before you watch the next one. All right, guys, talk soon. Bye.